All right. Chats there. All right. Can you hear me? Anyone hear me?
Yes.
All right, so I'm not going to use class time on this, but a complaint has come up that I do too much math in this class.
What? Too much.
Wait, really?
Too much math in math methods?
The complaint is twofold. One, that you can't use physical intuition. And there's something to that. In solving a physics problem, you never rely solely on math. I mean, maybe you also have a sense that, you know, because of the way the force is acting, this particle should be slowing down rather than speeding up. So you check your math at the end, and if the math shows that the particle is slowing down, maybe you've done it right. If it shows it's speeding up, you've clearly done something wrong. That's a fair point. But the thing is that only gets you so far, because our intuition isn't always correct. And more importantly, our intuition might tell us that the particle is slowing down, but it won't necessarily tell us whether the particle should be slowing down linearly, as a constant decrease of velocity or speed, or exponentially, or whatever. So you have to actually get the math itself as well as the physical intuition. And there are people who have been saying to me that they feel like they're not so good at math. And all I can say about that is, okay, first of all, yes, it is possible to improve, work hard. The other thing is, if you really think you're not like so good at math, then this is probably not the major for you. I mean, nobody would say, you know, I want to major in French literature, but I'm not so like good at, you know, like all those verb conjugations. I mean, okay, it's one thing to say, all right, I'm going to take some French my first year of college, and you take French, and if you do really well at reading and writing the language, then you think, yeah, I want to go further in studying and using this language. But if you're grinding through your first year or two of French with just C's, and you're always a little bit fuzzy on those verb conjugations, well, maybe reading a really big, complicated novel isn't for you in French. And then, you know, nobody would be shocked if after a couple of years of just basic study of the language, someone then said, okay, now we're going to read a really complicated novel. And the person said, yeah, I'm not so like good at like, you know, like those verb conjugations. And yeah, I'm not so like good at that. The French professor would say, well, yeah, then why did you decide to take a major that will require you to do things with French verbs? And look, if you find math intimidating, you've got three choices. One, you can just buckle down and get through it and like really crush it anyway. Sometimes that works. Two, you can at least do well enough that you do respectably. Please, for the love of God, don't talk about grad school. I mean, I know all the things we're supposed to say. There's a bunch of people in the physics community who want me to say, well, you know, math, I mean, physics isn't that mathematical. The first thing that happened to me when I was hired here is that they signed me up for an indoctrination camp. I mean, educational workshop on new teaching methods, where they said that conceptual understanding is so much more important than math. Well, of course, conceptual understanding is important, but the power of physics is not that we don't just say, oh, well, the particle will slow down in this case, or the light is going to be focused. We say the particle will slow down this much. We say the light will be focused to a spot of this size. We say that those photons will be absorbed at this rate, and that when they're absorbed at this rate, they will impart that much energy to the thing that's absorbing them. That's the power of physics, and that requires math. There's a bunch of progressive types who will say, well, you know, you don't really need that. And there's a lot that they're wrong about. And then they'll say, well, yeah, okay, so somebody did really badly on all these tests of math, but you know, the tests tell you this much. In the rest of the world, no one says, well, you know, the tests are bad. What are we Americans afraid of? Well, let's see. Well, first of all, we're afraid of Iranian nuclear physicists. And I can assure you that in Iranian universities, they don't say, the physics students don't get to go up to the professors and say, I'm not so like good at like, you know, like the math, like, because nobody wants the guy working on the nuclear weapons project who says, yeah, so like the neutrons, like they're in the material, like I know like they're absorbed, but like I don't really know like the numbers for that. You don't build a bomb by saying, yeah, like the neutrons are like absorbed. Now, by the way, I'm not making a geopolitical comment on whether Iran's nuclear program is that far along, who did or didn't violate what treaty, and whether or not the geopolitical implications of it are what people say they are. I'm just saying that we're afraid of this. Well, you know what? The people we're afraid of, they don't do all this. I'm not so like good at the math, man. What else are we afraid of? We're afraid of Russian hackers. Well, I can assure you that nobody in Moscow is saying, I was going to hack into election computer, but breaking through cryptography requires lots of math, and math is not what I am good at. It's very hard math. I don't know how to like, you know, decrypt and break through code, so I not hack election computer. Nobody said, okay? Nobody would hire that guy. So I said, yeah, I'm not so good at like breaking through encryption. It's too much math. I don't know how to break through encryption. Then they'd say, all right, well, you know, idi nachui to you. We're going to go hire someone else who doesn't talk all this fignia. Sergey, you come here. You break through the election computer. All right? You know, this is the world we live in. And we're afraid of the virus. Well, I can assure you that right now, even though most labs are shut down, some physicist somewhere is working on an X-ray scattering experiment to study a protein produced by the coronavirus. And if the person who's setting up the beamline says, I'm not like, you know, like the math, like I wasn't really sure like with the angles, I will tell you exactly what the virus will say to that person. Viruses don't talk. Oh yes, viruses talk. Viruses make noise. Here's the noise they make. That's the noise that the virus makes. And the virus will keep making that noise until we figure it out. And I can assure you that all the statisticians working on those clinical trials don't get to say, I'm not so like good at the math. All of the chemists involved in doing the synthesis and quality control and calculations needed to make sure that this stuff works. They don't get to say, I'm not so like good at the math. There's just a whole world out there that doesn't say that, that doesn't think that doesn't think that that's like an acceptable excuse. And if you think that physics is the place to come and be like, I really get the concepts, man, but like, you know, the math is hard. Well, yeah, there's a word for those people, crackpots. They're the people who end up sending me those essays on how they've come up with a theory of space and time that proves Einstein wrong. They just can't quite explain his math, or they can use a bunch of big words from a math book, but they can't actually do a calculation that correctly predicts how light will be bent by the sun's gravitational field. And yet they claim to have revolutionized space and time. And so I guess my takeaway is this is physics. Physics involves a lot of math. And I hope I never wind up having to do that rant again, but sadly I know I will. So with that, let's get to something a little more pleasant. I'm going to go over one problem from yesterday's homework, and you are going to tell me which problem I should go over. So let me set up the Zoom poll. Wait. Okay, there's the poll. All right. You tell me which of these questions I should be going over. You still see the poll?
Yes.
My screen is weird with Zoom, so I'm going to let that go for a moment. Give you a few more seconds. Please vote on which problem I should go over. Okay, well, it's pretty clear that people want me to go over the problem on adding oscillations, which is what I got a lot of questions about yesterday. So I guess that's not a surprise. Okay, can people see my writing tablet?
Yes.
Yes, sir.
Okay, so we're going to be adding two oscillations. We're going to be adding √2 cosine of omega t plus √2 cosine omega t plus phi2. And all of this has to equal something with amplitude √5, and it'll be another cosine of omega t with perhaps a different phase. That's what we need to do. Now, we could do this with trig identities, but that would be quite challenging. We'd have to go through a lot more hoops. I'm going to do this by noting that the cosine is always the real part of an exponential. And this is the real part of e to the I omega t e to the I phi2. And this is the real part of e to the I omega t e to the I phi3. And so then we're just going to add up a bunch of these things. We're going to have on the left side the real part of √2 times 1 plus e to the I phi2 e to the I omega t. And on the right side, we're going to have the real part of √5 e to the I phi3 e to the I omega t. So the thing I'm taking the real part of here has to equal the thing I'm taking the real part of here. So √2, 1 plus e to the I phi2 e to the I omega t equals √5 e to the I phi3 e to the I omega t. You cancel the e to the I omega t. And now at this point, we've got what looks like one equation and two unknowns. But remember, the left side has a real part and an imaginary part. And the real part of the left side has to equal the real part of the right side. And the imaginary part of the left side has to equal the imaginary part of the right side. So we actually have two equations. But now I'm going to get rid of one of the unknowns by multiplying both sides by their complex conjugate. So I'm going to multiply the left side, √2, 1 plus e to the I phi2 times √2, 1 plus e to the minus I phi2 equals √5 e to the I phi3, √5 e to the minus I phi3. And you may be thinking I multiply each side by something different, but remember, because the two sides are the same, this is the left side complex conjugate. This is right star, the complex conjugate of the right side, but the left side equals the right side, so this is equal to left complex conjugate because these two sides are equal. So what I'm left with is 2, and then I do FOIL to multiply all of these, and I get 2 plus e to the I phi2 plus e to the minus I phi2. And you're thinking, where does the 2 come from? It comes from the fact that I get 1 times 1, and e to the I phi, e to the minus I phi, those cancel. And on the right side, I just get 5. And whenever I add e to the I something plus e to the minus I something, I get 2 times the cosine of that. So I'm left with 2 times 1 plus cosine phi2 equals 5. Or cosine of phi2, 1 plus cosine of phi2 equals 5 over 2. Or cosine, oh, no, that should be 2 times 2, sorry. Because there were 2's in here, and then there's another 2 outside from squaring the square root of 2. So I get that cosine of phi 2 is equal to, this is 1.25, 1.25 minus 1, or 0.25. Any questions?
Yeah, Professor.
Yeah.
I was working it out with, I went halfway through and then I switched back into trig functions, and there's an infinite number of, or at least it seems like, phi's and, or phi 1 and phi 2's, phi 2 and phi 3's that will make this work.
Well, sure, because you can always add 2 pi to the angle.
Oh.
It's the same thing.
Thank you, my bad.
But adding 2 pi to the angle doesn't actually change its physical meaning. Anything else? Does anybody perchance recognize what this might be from? This requires you to have been way too into Twitter this summer. And I confess that I got a little lazy. So
I'm
on
sorry.
Twitter,
What's the question, Dr. Small?
anybody recognize what this problem might be from? That this problem might be a reference to something that was way too popular on Twitter this summer?
Oh, no, I don't have a Twitter account.
Okay, that's probably for the better. So the energy of an oscillation is the square of the amplitude. So if the amplitudes are square root of 2 and square root of 2, and the combined amplitude is square root of 5, then the energies initially are equal to 2 and 2, and the combined energy is 5. And you're thinking, well, wait, how is that possible? Remember that in order to combine these two things, I have to be applying some forces in order to combine them. So that's how the energies might not be added. Because when you add two oscillations, they could cancel out. You could have a very strong positive oscillation, a very strong negative oscillation. They cancel out to nothing, or they can interfere constructively or anywhere in between. And there was this big debate over the summer on Twitter about whether 2 plus 2 can ever equal 5. And the answer is no, 2 plus 2 is never 5. And then somebody starts saying, I'm not like so good at like the math, but 5 is like close. Sorry, no. Okay. 2 plus 2 is never 5. But you can combine two things that have measure 2 and get a thing that has measure 5 or measure 3 or whatever else. You just can't say that, hey, I was adding numbers, because you weren't adding numbers. You were combining two oscillations, which is much more complicated than adding numbers. But I saw that and I thought, hey, wait a minute, I could come up with a situation where we combine two oscillations that each have energy 2 and get an oscillation with energy 5. I'll put that on the homework. Okay.
Dr. Small, I still have a question about that that problem right over there.
Okay.
So halfway through, I understand why you said that you could just multiply both sides by the complex conjugates, but how does that translate to phi sub 2 equaling phi sub 3?
Did I say phi sub 2 equals phi sub 3? Where did I say that?
Oh, no, well, at the end when you just solved, you just solved for phi sub 2 equals, or cosine of phi sub 2 equals 1/4.
Yeah. Yeah, cosine
and then
equals 1/4. I never said cosine of phi 3 is 1/4. Did I say that?
Oh, no, I was just wondering because the question also asks for cosine phi 3.
Okay, well, once you've got cosine of phi 2, then it's fairly trivial, because we know that e to the I phi 3, root 5 e to the I phi 3 equals root 2 times 1 plus e to the I phi 2. And so this would be root 5 cosine of phi 3 plus I root 5 sine of phi 3 equals root 2 plus cosine of phi 2 plus I, sorry, phi 3, my bad, plus I sine, no wait, that should be phi 2, my bad, plus I sine of phi 2. And then I think you can go from, oh, and there should be a root 2 there and a root 2 there. And then it's just a little bit of algebra from there. Anything else?
Thank you.
Okay, so at the end of last class, I outlined how you would do, or where a multivariable Taylor series comes from. The multivariable Taylor series would be a combination of many different derivatives. But in practice, we don't necessarily do it that way. We don't necessarily have to, I mean, it's equivalent to taking a whole bunch of cross partial derivatives. But here's what we usually do in practice. Let's say that f of z and t was e to the minus gamma t over square root of a squared plus z squared, which is something that might come up in the theory of diffusion. And let's say that I wanted to figure out what this would be for small t and small z. What I would probably do is, since this is a product of a function of t and a function of z, and you may be thinking, wait, isn't that a ratio? Well, sure, but this is e to the minus gamma t times 1 over square root of a squared plus z squared. I could just expand this and expand this. And this would be 1 minus gamma t to lowest order. Why did I write alpha? 1 minus gamma t. And this, let's review that trick. This is going to be the square root of a squared, sorry, 1 over the square root of a squared times 1 plus z squared over a squared. This is a, sorry, 1 over a times 1 plus z squared over a squared to the minus 1/2. You're thinking, why minus 1/2? Remember, square root is the 1/2 power. And when you have 1 over something, the power becomes negative. And we know that 1 plus x to the n is approximately 1 plus nx. Here, x is z squared over a squared. N is minus 1/2. So this whole thing becomes 1 over a, 1 minus z squared over 2a squared. Any questions? No questions? All right. Then today's main topic is going to be integrals in polar coordinates. But before we do them in polar coordinates, I want to review multidimensional integrals in, or multiple integrals in Cartesian coordinates. I'm not going to do an exhaustive review of multiple integrals. There's this class called Calculus 3. You allegedly took it, you allegedly passed it, and we're all just going to pray that you remembered some of it. But here we've got our x, y, and z axes. And let's say that we want to find the volume of this pyramidal shape that goes out a distance 1 on each of the axes, right? Well, we have to do 3 integrals. So let's start by integrating along the x-axis. The problem we run into is, okay, fine, x goes from 0 to 1. But then y, well, let's see, what could y be? Y could be potentially, if x is 0, y could go all the way to 1. If x is, say, 1/3, well, y is not going all the way out to 1. It's going out to, at most, 2/3. So that's 1 minus 1/3. But it might not even be going out that far. If we're up there, it's going to go out an even shorter distance. But the absolute farthest we could possibly go is 1 minus x, and often we'd be going out less than that. And then z, well, z can only go out to 1 minus x minus y. And we're going to find the volume, so it's just dx, dy. All right, I guess I should reverse the order. dz, dy, dx. And the single most important thing I want you to remember from this is that when you do this integral, you are plugging in at the end whatever this formula might be up here, even if it's not a number, but a bunch of symbols. We work with symbols in physics, just like we do verb conjugations in French and Spanish, and we do tons of noun declensions in Russian. So this would be the integral from x equals 0 to x equals 1, from y equals 0 to y equals 1 minus x. And the integral of dz is just z. Z evaluated from 0 to 1 minus x minus y. And when we put all that together, we are now integrating from 0 to 1, and y from 0 to 1 minus x, 1 minus x minus y, dy, dx. And there are always people who say, isn't there like some sort of shortcut? No, there are no shortcuts. All right, these first two terms, do you see a y in either of these two terms? I don't.
I don't either.
Yeah, so if there's no y in there, then these two terms are constants. You may be thinking, wait, x isn't a constant. Well, x isn't a constant when we're integrating over x, but x is certainly a constant when our variable of integration is y. So we're going to have 1 minus x times y. Minus, now y does depend on y, and the integral of y is y squared over 2. And all of this gets evaluated from 0 to 1 minus x. And whatever we get out of that will then be integrated over x. So we get the integral from 0 to 1 of 1 minus x squared, because 1 minus x gets multiplied by 0, and then it gets multiplied by 1 minus x, minus 1 minus x, whole thing squared, over 2 dx, or the integral of 1 minus x squared over 2 dx from 0 to 1. And then that's just the integral of 1/2 times the integral of 1 minus 2x plus x squared over 2 dx 0 to 1, 1/2 times x minus x squared plus, oh wait, I shouldn't have had that 1/2 there because I got the 1/2 there, plus x cubed over 3 from 0 to 1. So you get 1/2 of 1 minus 1 plus 1/3 or 1/6. And if you take nothing else away from this, take away that when you do a multiple integral, oftentimes the limits on one variable will depend on the limits on another variable. And for this case, everything's linear. It's not that big of a deal. We'll get to one case that is a big deal in a moment. Any questions though first?
Can you go over one more time how you picked the limits of integration for z?
Because this plane here is defined as x plus y plus z equals 1. That's the equation of this plane.
Right.
As soon as I know x and y, z has to be 1 minus x minus y.
I was going to ask this question. Will you, I mean, I'm assuming you won't, but will you be giving us the equation of the plane, specifically in terms of z?
Next chapter, we're going to go over analytic geometry.
Okay.
A topic that was allegedly covered in Calc 3. And since I've been told to assume the best of everyone, I have a problem here. Either I assume the best of you and the worst of your Calc 3 professors. You learned everything that your Calc 3 professors taught, and they just didn't teach these topics. Or I assume that your Calc 3 professors were drunk on the job and didn't do it. You can tell me which one of those I should assume. But yes, we will review the equation of a plane when we get to a subsequent chapter.
Got it. Thanks.
Other questions? And yeah, I know that was kind of snide, but look, here is the fundamental problem in physics. The fundamental problem in physics is that everything builds off of everything else. Newton, not exactly a humble man, said that he stood on the shoulders of giants, referring to people like Galileo. Galileo couldn't have done what he did unless there had been a long tradition of good optics for telescopes, and there had been a long tradition of deductive and inductive reasoning in mathematics. All of that went back to the Arabs and then the Greeks. You cannot do advanced E&M without introductory E&M. You can't do advanced E&M without a lot of math. So if at every stage we constantly have to be like, okay, it's senior year now, let's think back to freshman calculus. At some point, things from previous classes have to become ingrained in your mind. This is a cumulative subject. All right, at some point, prior have to be stuck in here. Otherwise, you can't keep advancing.
I don't disagree.
All right, so we can do more multiple integrals than that, but when we get to complicated shapes, like let's say I want to integrate over a circular domain, well, x squared plus y squared, I can do better than that. X squared plus y squared equals big R squared. So y is the square root of big R squared minus x squared. So if we wanted to find the area of this, well, one thing we could do is remember that the area of a circle is pi r squared. Insert joke about memory here. Or we could integrate from x equals, minus r to plus r, and from y equals minus square root of r squared minus x squared to y equals plus square root of r squared minus x squared dy dx. Now, those are integrals that we can do, but they get messy. And one of the ideas of polar coordinates is to make these integrals easier, to work in a different coordinate system. So remember that in polar coordinates, I'll go to the next page. Instead of talking about x and y, we still have x and y axes, but the way we specify a point is via the angle. Some books call it phi, some call it theta. Phi is more popular in physics. And the distance from the origin. And r is just the square root of x squared plus y squared. And phi is either the arctangent of y over x or pi plus the arctangent of y over x. You're thinking, well, which is it? And the answer is you have to actually think, because here the tangent is positive. It's positive y over positive x. Here, the tangent is also positive, but x and y are negative, so you have to think it through and figure out which it should be. That's one of the drawbacks to polar coordinates. Certain formulas don't automatically work. Certain formulas require you to be very careful and plug in an extra plus pi occasionally. But certain other formulas become very simple. And x is our cosine phi, y is our sine phi. Okay, so we want to do an integral, but if we just simply integrate r equals r1 to r equals r2, phi equals phi1 to phi equals phi2, if we just did dr and d phi, very naively, this looks like how you do an integral. You've got a differential of each variable. But if we start thinking about coming up with a differential area element, remember that if I'm say out here, and I go over a distance dy and a distance dx, I've got a little area element here. And dA is dy times dx. The area of this little patch is the width multiplied by the height. On the other hand, and now this is one place where you can use physical intuition, the units of dr times d phi are not area units. So we have to think back to Calc 3 when they allegedly covered this. And I'm going to first tell you the answer. And hopefully when you see that it's r dr d phi, a little, oh yeah, will go off in your head. I remember that. Then I'm going to derive it in two different ways. The first way I'm going to derive it is the most intuitive geometric way. And then I'm going to plug into a formula that the book asserts, but we don't really yet have the tools to derive. We're going to have to use something called a Jacobian Matrix, which we will get to sometime later this semester. But for now, I will plug into the formula that they assert just to verify that the pieces fit together, even if I haven't yet told you where all the pieces come from. So let's say that we are looking over an angle d phi. All right, and we go out a distance from r to r plus dr. So the thickness in this direction is dr. And then the question is, what is this width? What is this little dw, this little differential width? And then we have to remember that the arc length along a circle, some people would call it ds, is r d phi. And where that comes from is that we could think of this as a little segment from a much larger circle that would have circumference 2 pi r. But we're not taking that entire circumference. We're just taking a little fraction. Sorry about that. There's this button on my pen. The fraction we're taking is d phi over 2 pi. So the fraction times circumference is d phi over 2 pi times 2 pi r. 2 pi's cancel, and we're left with r d phi. So dA would be dr times r d phi. Questions? Any questions on where that geometry comes from?
Just for clarification, the DW is that little block that you have colored in, right?
Yeah, it's just this part.
Okay, cool. Thank you.
Any other questions? All right, the other way that the book asserts is they use something called a Jacobian matrix. They say that dA, this is, I am not going to derive it today. They say that dA equals dx dy times the determinant of partial x, partial r, partial x, partial phi, partial y, partial r, partial y, partial phi. Let's check that. We know that x is r cosine phi and y is r sine phi. So that's got to be dx times dy. And then we do a determinant, which is we multiply these and then we subtract off that product. But let's first make the elements of that matrix. Well, the derivative of x with respect to r would be cosine phi, and the derivative of y with respect to r would be sine phi. And the derivative of x with respect to phi, we've got r times the derivative of cosine, which is minus sine. And I just realized, no, it should be dr d phi out here. So the derivative of x with respect to r is minus r sine phi, and the derivative of y, well, y is r sine phi, the derivative of sine is cosine. So we get r cos squared phi plus r sine squared phi. Cos squared plus sine squared is 1, so we're left with r dr d phi. Any questions?
In your matrix, the bottom half or the bottom row, that's dy, dr, and dy, d phi, right?
Yeah.
Okay, cool. Thank you.
Let me erase and redo those. Oops. Partial y, partial r, partial y, partial phi. Okay. So now, first thing we should always do when we learn a new technique is we should check it on the simplest problem we can think of. And the simplest problem I can think of is the area of a circle. So we would be integrating from r equals 0 to r equals big R, and from phi equals 0 to phi equals 2 pi. And the beauty of this is that whereas before our limits of integration depended, the limits on one variable depended on the limits on the other variable, now they don't. Now our limit of integration on r is just 0 and r. Our limit of integration on phi is 0 and 2 pi, because in this coordinate system, physicists like to say that this coordinate system reflects or respects the symmetries of the problem. We have a circularly symmetric problem, and we likewise, in circular symmetry, the boundaries of one coordinate have no bearing on the boundaries of the other coordinate. So we've got, and technically I should be reversing the order in which I list these. Okay, in this integrand, I don't see a phi anywhere. Does anyone else? So if there's, if there's no phi in here, then the integral over phi is just going to be 2 pi. So then we're just left with r dr. And the integral of r dr is r squared over 2, which cancels the 2 into 2 pi, from 0 to r, and we've got pi r squared. And that is indeed the area of a circle. So we can have some confidence that this technique probably works because it reproduces results that we already know in a simple case. Any questions?
Yeah, if we were to try to derive the circumference of a circle instead of the area, would we only have one integral?
Yeah, and then what you'd have to do is we'd have to do a line integral. So what I would probably do is parameterize it. I would probably, rather than trying to derive it, if you really wanted to do it without just simply asserting the result known since the Greeks, here's what I would do off the top of my head. I would start off still with r and phi. X is equal to r cosine phi. Y is r sine phi. And then I would say that we're going to do an integral over phi. We're going to have some element as we go out a distance d phi. We're going to be making, I'm going to zoom in on this triangle here. All right, we're going to have dx and dy. This will be the square root of dx squared plus dy squared. And dx, if the only thing that changes is phi, if r does not change, there's a big if. Some of you are thinking, wait, before we were treating r and phi as variables, why is he not treating them as variables here? This is if r is constant, then dx is just partial x, partial phi, d phi. dy is partial y, partial phi, d phi. And so we are going to have here that dx is, let's see, x is r cosine. So we're going to have minus r sine phi, d phi. And then dy will be plus r cosine phi, d phi. And so all of this becomes the square root of r squared sine squared phi d phi squared plus r squared cosine squared phi d phi squared. You can pull out the r. We can pull out the d phi. Cos squared phi plus sine squared phi, which is 1. And so I would be left with r d phi, and then I integrate that from phi equals 0 to 2 pi, and I get 2 pi r. Make sense?
Yes, awesome. Thank you.
All right, that's how we do it from first principles. But there is some value in knowing how to derive first principles. All of those epsilon and delta proofs that you learned in freshman calculus, and then being physics majors, this part I'm not going to mock you for. Being physics majors, you said, look, we need to use it. We don't need the proofs. So you forgot the epsilon and delta proofs and just focused on memorizing derivatives. I love memorization. Those who say that memorization is the lowest form of learning, forget that it's still a form of learning. But all those epsilon and delta proofs matter as soon as you try to learn more advanced algorithms for solving equations with discontinuities. Then it all comes back. So there is a value in being able to do things from first principles, but there is also a value, since we're not doing anything with the discontinuity here, there is a tremendous value in just memorizing the circumference. But yes, good question. How would you derive the circumference from first principles? And I've kind of cheated there because the very idea of defining a system of angles where your maximum angle is 2 pi comes from already knowing that the circumference is 2 pi r. And those derivatives of trig functions come from a system of knowledge developed where people already understood trig functions in terms of circles. So all I really did there was show how the elementary pieces fit together. I actually didn't derive the elementary pieces from pure logic there. A math professor could pick it apart on those grounds. But I'm not a math professor. I'm just showing you how physicists do this. Okay, let's do a different problem in polar coordinates. Let's do the problem of finding the potential energy when we have a point object interacting with a surface. We're going to say that it's a distance z above the center of the surface. And that if I just looked at the potential energy between this thing here and this thing down here with a little area dA, the potential energy would be minus dA. I'm going to call this distance S instead of R. And the reason I'm calling it S instead of R is that this little element is the distance R from the center. Minus dA times sigma, surface density, usually like a charge density, over S to the oops. Over S to the N, where N could be whatever. And if we were in E and M, what would N be? Any guesses? Does anybody remember what the potential energy between 2 point charges is?
Some fraction, like
A Q over R squared.
Oh, the energy is 1 over R squared? I thought it was the force. You know what I'm going to do? I'm going to go to the next department meeting and I'm going to tell the faculty we should start requiring Physics 1520. And look, I promise I won't turn every day into one of these gripe sessions about remembering, but the point is that everything in physics builds off of everything else. How can we even do a class on math methods for physics if you don't remember the physical contexts in which we would be using this math? You have to remember things. So in E and M, for electrostatics, N would be 1. The potential energy is 1 over the distance. But I'm not just going to do the E and M problem today. I'm going to do the general problem, and then we'll go into the E and M problem. Because there are actually really important contexts in physics where I'm reaching under my desk. No, I left that book in my office. They're actually really important contexts in physics where n is something else, like van der Waals forces, the forces that dominate on the microscopic scale, the forces that dominate a lot of interactions between molecules in chemistry and biology. There, n is 6.
Wouldn't n be like the number density, something like that?
The symbol n can be used for a density. It can also, the symbol n gets used for a lot of things. Sometimes it gets used for a number density. Sometimes it gets used for refractive index. Sometimes it gets used for an exponent. But if you prefer, I will get rid of n and we will replace it with, let's see here, k is also used for an arbitrary constant. It's used for wave number. I will use v because it's not going to show up anywhere else in this problem. I should warn you, I wrote the homework set with n, but for now, we'll use v. We're going to do it for something arbitrary because v equals 6 is really important. All right. And sigma is a surface density. We're going to use rho for a number density in 3D. Okay. That's the potential energy between this object here and this little element of the surface. I want to know the total energy. So that's going to be the integral over the surface, or the integral from r equals 0 to big R. And the integral from phi equals 0 to 2 pi minus sigma. I'm going to pull out all the constants in front. I'll just give myself a little more room there so that the sigma is somewhat legible. R dr over d phi s to the v. Okay, but what is this s? Well, now we've got to do some trigonometry. And s is going to be equal to the square root of z squared plus r squared, because this is a right triangle here. Z is perpendicular to the surface, r is in the surface, s is the hypotenuse. So what we've got is minus sigma double integral r equals 0 to big R, phi equals 0 to 2 pi, r dr d phi that. Now, there are two variables that we're integrating over, but again, because it's a circular problem, I don't see a phi in the integrand anywhere. So I can pull out that integral over phi. I could just do it, and I immediately get minus 2 pi. I'm not going to bring out the 2. I'm going to do minus pi sigma integral from r equals 0 to big R, 2r dr over z squared plus r squared to the v over 2. And the reason I'm going to do that is, well, what is 2r dr the differential of?
The differential of the
R squared.
Of the what? The spread? What is the spread? Two different people were talking. One of them got cut off, and then the other one just said the spread, which I couldn't quite understand.
He said r squared.
R squared, my bad. Yeah, this is dr squared. It's also the differential of z squared plus r squared, because that z squared is a constant. So I'm going to call this u. We've got du. And then we've got the integral of minus pi sigma. Well, when r is 0, u is z squared. And when r is big R, u is z squared plus big R squared. And so we've got du over u to the v over 2. Or minus pi sigma integral from u equals z squared to z squared plus r squared, u to the minus v over 2 du. And the integral of a power is just the same thing to that, to a one higher power divided by the one higher power. So that is minus pi sigma over 1 minus v over 2, u to the minus, sorry, to the 1 minus v over 2 from z squared to z squared plus r squared. Or minus pi sigma over 1 minus v over 2. I almost wrote a v squared because I'm so used to squaring v, times minus, let's see here, z squared to the 1 minus v over 2. That would be z squared times that's minus pi sigma over 1 minus v over 2 times z squared plus big R squared to the 1 minus v over 2 minus z squared times z squared to the v over 2. So we just get z squared times z to the v. Okay, let's think about some cases here. Let's say that v equals 6. If v equals 6, then what we've got here is minus pi, that's the van der Waals force, which is a force between electrically neutral objects made out of little atomic dipoles, minus pi sigma over 1 minus, well, v over 2 is 3, so 1 minus 3 times z squared plus r squared. Again, v over 2 is 3, 1 minus v over 2 is negative 2. There should be a big R squared. If big R goes to infinity, you know, we make this circle over here go out wider and wider. What's 1 over R squared to the 1 over R squared squared?
That's 0.
Yep, this is going to 0. Minus z squared times z to the 6th. I feel like I'm...
Would that be a minus 6?
Oh, yes, thank you. All right, so that is going to be, let's see here, we're going to have, all of this is pi sigma over 2 times negative z to the negative 4th, or minus pi sigma over 2z to the 4th. All right. Well, where do we go with this? Okay, so I've derived a formula. I've derived that if I have a 1 over r to, or 1 over s to the 6th potential between a point object and a little piece of a surface. When I integrate over the entire surface, I get 1 over distance to the 4th power. That has practical applications in biology. If I were to consider a molecule very close to a membrane, that would be an important thing to know. On next week's problem set, you're going to then have to integrate over a volume. You're going to have to say, okay, there's a surface here that goes out to infinity. Below it, there's another surface. Below it, there's another surface. Below it, there's another surface. So you have to integrate that. So we can go further with that. It's of some practical relevance there. It's also a general technique. There are other situations where you're going to have different kinds of forces, sometimes hypothetical forces. People are doing experiments to look for new forces. Well, let's consider another case. Let's go back to the case that V equals 1, right? Because that is the case in electromagnetism. So in E&M, what we've got is, well, let's see here, V equals 1, V over 2 is 1/2, 1 minus V over 2 is 1/2. So in E&M, we've got minus pi sigma over 1/2 times Z squared plus R squared to the 1/2 minus Z squared times Z to the minus 1/2. Yeah, because that should be, I feel like I've done something wrong here. Does anybody see what I've done wrong? I know I've made a mistake in here because I'm looking at my notes and it's different. And I'm just trying to figure out where the mistake was. Z squared to the 1 minus V over 2 is,
The Z to the negative 1/2 should be positive, right? Is that it?
should just be Z to the,
It should be 0, no?
oh, because it was 1 minus V, so it should be Z to the 2 minus V. Okay. So this should be 2 minus V up here. So that should be 2 minus 1. Okay. So we get this. We get 1 over 1/2 is 2. So we get minus 2 pi sigma times Z squared plus R squared to the 1/2 minus Z. All right, now if we take R to infinity, this time we have a problem. We didn't have a problem when we considered the van der Waals force, but this time it looks like we have a problem. It looks like our potential energy is blowing up. Well, let's just play with this a little bit. Minus 2 pi sigma, and there should be a 1 over 4 pi epsilon naught, but we're working in grown-up units. Let's do the trick we've been doing, that Z squared plus R squared to the 1/2 is R times 1 plus Z squared over R squared to the 1/2. the Taylor series trick that we talked about last time, minus 2 pi sigma times r times 1 plus 1/2 z squared over r squared minus z, or minus 2 pi sigma r minus pi z squared sigma over r minus z. Well, this term goes to 0 as big R goes to infinity, so that's fine. Now, do we actually measure energy directly, or do we measure changes in energy? We really only measure changes in energy. Every experiment involves a change in energy. You heat something up, you cool something down, you change the motion of an electron. At the ultimate level, every experiment is about a change. And so changes in energy are related to forces, which are derivatives of energy. And what's the derivative of R with respect to Z? Does R depend on Z?
No. Wait.
So go ahead. No, but?
Are you talking about the expression you just derived on the bottom?
Yeah. When we look at this expression here, there are 3 terms, and this one's going to 0. This one, does it depend on Z?
It shouldn't.
Nope. This is the only term that depends on Z. In this term, its derivative is nice. So partial U, partial Z is just 2 pi sigma. And I probably made a few mistakes with minus signs. There are many minus signs coming and going in this. But you see how this derivative is a constant? And we know that the electric field of an infinite sheet charge is a constant. So we did this integral in polar coordinates, and we got an expression, which I then messed up the exponents in, because I was doing it in a hurry. But then when we took the limit of large R, we had something that at first looked like it was going to blow up. But then we take that and we expand it to isolate the R, the thing that's blowing up. We find that when we isolate the thing that's blowing up, we get one term that, yeah, it depends on Z, but it's going to 0. Another term that's blowing up, but it doesn't depend on Z, so it won't show up in any derivative. And there's only one term that's actually going to show up in a derivative, and it's nicely behaved. And this care and feeding of infinities is an important topic in physics. It's a topic that goes all the way into the deepest realms of theoretical physics. That's why I spent some time on it today, because this integral in polar coordinates shows us an infinity that has to be very carefully treated. Any questions? Okay, we've got about 8 minutes left. What I'm going to do in the next 8 minutes is I'm going to start something that's on next week's homework. And then on Friday, I'll probably need about 15 minutes to go over it. And then after I do that on Friday, you'll have the rest of the time to work on a Taylor series activity. I want to do one more polar coordinates integral. It doesn't start as a polar coordinates integral. It starts as an integral that before I just asserted. I just told you that the integral from minus infinity to infinity of e to the minus x squared dx is the square root of pi. And now I'm going to show you where that comes from. Let's start by squaring this. So I'm just going to multiply it by itself, except that when I multiply it by itself, one of them will just be the same thing as before, e to the minus x squared dx. The other thing is going to be e to the minus y squared dy, because if these are just two isolated integrals, yes, I named the variable x in one of them, and I named the variable y in the other one, but What's in a name? That which we call x would by any other name still be a variable of integration. That which we call x would by any other name still cause this integral to converge. And so we still have a convergent integral. We have the same integral twice. I just used some different names. But now, because I'm multiplying these two integrals with integrands that depend on different variables, there's nothing to stop me. If I call this I, I'm going to call this I squared. There's nothing to stop me from combining them. Oops. Now, what does that exponent look like in polar coordinates?
That is negative r squared.
Yep.
And then the differential elements would again become r dr dphi.
Yep. So I've got the integral from r equals 0 to infinity of r e to the minus r squared dr, integral from phi equals 0 to 2 pi d phi. This is just 2 pi. So I've got pi integral from 0 to infinity of 2r e to the minus r squared dr. If I do a u substitution, u is r squared, du is 2r dr. Hey, look, I've got 2r dr in here. So I've got pi integral from u equals 0 to infinity e to the minus u du, which is pi times minus e to the minus u from 0 to infinity, or minus pi times 0 minus e to the 0, or 0 minus pi times 0 minus 1, which is just pi. And that is an integral worth doing and worth memorizing because it shows up all over the place. It shows up in statistics, shows up in quantum mechanics, shows up a lot in optics because many beam profiles, many focused laser beams have profiles that you can approximate with this. Shows up in signal processing because a lot of packets of information have a spectrum that's kind of sharply peaked at one frequency, and so you can approximate it as Gaussian. So it shows up all over the place. It's an integral worth memorizing. Any questions on how I got it?
Yeah, can you clarify for me how you did the change of integrations from negative infinity to 0 to 2 pi and like 0 to infinity?
Well, because we're integrating over the entire plane. We're doing an integral in polar coordinates over the entire plane. And if we're integrating...
Oh, okay. Okay, yeah, I understand now. Thank you.
You're welcome. By the way, besides my 3 or 4 usual suspects, the rest of you are welcome to ask questions as well. There isn't a rule that only 3 or 4 people are allowed to ask questions. It's not like they paid for the premium subscriber tuition and the rest of you are just getting the cheap entry-level Patreon subscription. You're allowed to ask questions as well. Now, there are more integrals like that we could do. We could do the integral from minus infinity to infinity of x squared e to the minus x squared dx. And that also shows up a lot in statistics and quantum mechanics and whatnot. And one way we could do this is integration by parts. That's tedious. We'd have to do several steps. But what if I started by making one little change? E to the minus alpha x squared dx, where alpha is a constant. We're going to set it to 1 at the end. Okay? We're going to do the integral with some arbitrary value of alpha, And then at the very end, we're going to set alpha to 1. Okay, well, that seems like we've just added another piece of work, except that x squared e to the minus alpha x squared is minus d by d alpha of e to the minus alpha x squared. Right? Because if I take the derivative of an exponential, I just get back the exponential multiplied by the derivative of the exponent with respect to alpha. And remember how in the first week on the activity, I had you do a bunch of integrals? Like I might have you do the integral of x e to the minus alpha x squared. This is one that you were able to do with the tools you had already learned. And sometimes it was over dx, and other times it was over d alpha. Do you remember things like that from the first week? And those are integrals that you could do just using tools from Calc 1 if you remembered Calc 1. Well, now we've got one that we can't do, but the lesson is that we're treating one of these as constant and the other one as a variable. And for these purposes, we're saying that for this purpose, alpha is the variable and x is the constant. So when I take the derivative with respect to alpha, I just get the minus x squared out front. So last thing, what I've got here is minus d by d alpha of the integral of e to the minus alpha x squared dx minus infinity to infinity evaluated when alpha equals 1, which is minus d by d alpha square root of pi over alpha when alpha is 1. And that is the square root of pi, or minus the square root of pi from that minus sign in front of the derivative, times minus 1/2, because we've got alpha to the minus 1/2. Alpha to the minus 1/2 evaluated when alpha equals 1, times minus 1/2 over alpha to the 3/2, evaluated when alpha equals 1. And when all the dust settles, this is square root of pi over 2 alpha to the 3/2 evaluated when alpha equals 1. And we are out of time, so what I'm going to do on Friday is I'm going to go over a few more examples of integrals like this because they're on next week's homework, and then we'll do an activity involving Taylor series. I'm not gonna, you're free to go now, but if anyone has questions, I'll stick around for a few minutes.
Thank you, Professor Small. Have a good day.
Bye.
I had a question, Dr. Small.
Yeah.
Are you always allowed to pass like a differential outside, like back through an integral sign if it's not with respect to that variable, like what you did on that last problem?
Am I always allowed to say that again? Something came up. Say that again.
You pass the d over d alpha straight through the integral sign. Are you always allowed to do that?
If you're taking a derivative, if the thing that you're taking the derivative with respect to is not something that you're integrating over.
Okay.
Because you can't simultaneously integrate and differentiate. You have to be very careful about the order of those operations. But if you're integrating over one variable and differentiating with respect to something completely different, then yeah, you can interchange the order.
Okay, thank you.
You're welcome.
Professor, I have a question. When it comes to the Gaussian integral, every time I search it up, they mention something about like an error function. What does that mean?
Okay. So let me move this. Sorry, there are still some controls I'm figuring out. Can you see my tablet screen again, my writing screen?
Mm-hmm. Yeah.
Okay. So if I just did the integral from minus infinity to x e to the minus u squared du, this is defined to be something called error function of x. And I think there's technically a 1 over square root of pi there. Right? That's defined to be something called the error function of x. It's just a name for the integral. And people have studied the properties of that integral. If you gave the, if you said, hey, this is actually the error function, well, that doesn't tell you anything. Right? It's just a name. You have to then go into the properties of the error function. Why is it called an error function? It's called an error function because these integrals show up a lot. And it's basically saying how, let's say that, you know, this integral, if I took it from minus infinity to infinity, would be equal to 1. But what if I didn't take it from minus infinity to infinity? What if I took it from minus infinity to there? So I'm leaving out all of that. I'm leaving out that area under the curve. How much area am I leaving out? That's the error. And because people oftentimes have to leave out part of the tails and they want to know what they're leaving out, how big is the stuff that they're leaving out. And for certain statistical purposes, that would be like an error. So they want to know what their error is. That's why it's called an error function.
Okay, sounds good. Thank you.
You're welcome. Anyone else have questions?
Yes. Oh, sorry, I'm hearing myself through a feedback loop right now because I have 2 accounts in the Zoom meeting.
That's fine.
On number 1, I had a question about, like, in class I said there was an infinite number of solutions, which even with yours there's, but can I share my screen for a minute?
Sure, I'll turn off my screen sharing. Stuck with the tablet and the meeting control. All right, I just stopped my screen share.
Thank you. Okay, desktop 2. There we go. Okay, that's appearing over there. When I go to when I was trying to do that problem, let me unplug my earphones. When I was trying to do that problem, I went to, well, at first I screwed up, so then I went to this little site that has a Mathematica type MATLAB equation solving system, and I figured out that what I was doing wrong, I was splitting up the E to the IWT, E to the phi, and when I would cancel one from one side to the other, it would kill this there's a sine squared times I squared part if you multiply E to the IWT, E to the I phi. And
well, it's not sine squared because it's 2 different sines. It's sine of omega t, sine of phi.
Wait, what? Sorry, I may have.
You said sine squared. If I multiply e to the I omega t by e to the I phi, I'm not squaring a sine. To square something means to multiply it by itself. I'm multiplying the sine of omega t by the sine of phi. So I'm multiplying 2 different sines. That's not a square.
Sorry, not. Anyways, it's a sine times a sine.
Okay.
But it'll get killed on where it shouldn't, is because. See, I go over here. Oh shoot. This is what you get if you have some equation solver solve this thing with trigonometry. You can get solutions like this, where phi doesn't necessarily need to be 0.25. It can be any number, and this is the square root 2 cosine WT plus square root 2 cosine WT plus phi 2.
Okay, I see the mistake you made. What you're assuming there, I mean, your solutions are right in a certain sense. They're right in the sense that there are moments in time where these 2 sides will be equal to each other for phases other than the ones that I chose. Okay, so if I just, what?
Oh, and I'm allowing phi3 to be a variable here? Okay, change over time.
No, what you're assuming is you're setting e to the I omega t times the first thing, or you're basically asking, what are these two functions equal to each other, allowing for the possibility, or you're basically asking what values of the phase would make these two functions equal to each other at a time t, at a time t, one time t.
Okay.
I want to know what makes these things equal to each other at all times t. So I have to cancel out the e to the I omega t. You didn't do that. And so I think that when you don't do that, you can introduce certain spurious solutions.
Okay.
Now I want these equal to each other at all times. That's the trick here.
All right, sounds good. Thank you. Sorry about the KQQ over R squared during the lecture. I was trying to get all this put into Desmos over here, and there was an awkward silence, so I just.
No, I mean, you're right that 1 over R squared is what shows up in E and M, but it shows up as the field, not the potential. That's the difference.
Thank you. Have a good day.
You're welcome. Ewan, do you have a question for me? All right, well, then I'm logging out.